Hello everyone, I'm Dr. Hussain Haidari, and today we're going to conclude our discussion on polymers with this last lecture of the asynchronous material. Today we're going to talk about a few final comments on additive manufacturing processes, as well as vulcanization, which is a process of cross-linking elastomer type of polymers. So, and then we're going to have a few more summary comments at the end. So today we're going to conclude the third week of our polymers series, and it's again going to be mostly focused on manufacturing processes. So before we talk about elastomeric materials and their cross-linking methods, let's finish what we started talking about last time. So, okay, so this process was, as you may recall from the last lecture, called DLP-based 3D printing, or DLP-based SLA, which is a subcategory of two-dimensional 3D printing processes. And the reason we call them two-dimensional is because you print, or in other words, you transform and cure material a layer at once. So you print the entire 2D layer in one process step, and then you move on to the next layer. And this is opposed to the cases where you do 1D or 0D sub-units at a time. So in the case of an FDM printer, you would do a point at a time, which is a zero-dimensional process, and you would then fuse these points together as you deposit material, and then you would move on to the next layer. And then we had the 1D processes, which would deposit an entire line at once. And then these that you can see here are examples of a 2D process, which prints one layer, an entire 2D layer at once, and then moves to the next layer. So yeah, this is one example of that, which is DLP printing. And the reason we call it DLP printing is that you use a DLP projector to project the 2D image, and the material here is a photosensitive material that, when it's illuminated with light of a particular wavelength, it solidifies, and then the material surrounding it, which hasn't been exposed, remains liquid. So you can actually solidify the polymer selectively using light. So the problem with this process is that as you're solidifying material can stick to your bottom window. So if you look at this image here, the window I'm talking about is down here. So it's underneath. It's under the liquid tank, basically, is a piece of glass. And this piece of glass is where the image comes through. Okay, so underneath this layer of liquid is a glass window, and that glass window is where light actually travels through and hits the material. So the problem with this is that as you expose, the material as it solidifies is going to stick to your bottom window, okay? Because as it cures, it actually cures onto the glass, okay? So the problem with that is that you have to figure out a way to peel it off. Now, a lot of these print processes have similar phenomenon that's happening here, and that is basically they do a pumping step, and it goes up and down, and it peels the object off of the membrane and then goes back down to print the next layer, and it has to do this pumping step and peeling process every time to detach the solidified object from the window, from the glass window, because every time it sticks to it. Now, another way to avoid that is to have a membrane or a window that is non-adherent to this material. So if it was actually, let's say, if this resin was water-based and the window was hydrophobic, it would actually naturally repel the molecules, and so they wouldn't stick even if they solidified. Now, this cannot be done in all cases for all materials, and finding a suitable glass window is always a problem. So although you may have not thought of this as a big challenge, it is actually indeed a very big challenge. So the challenge again that we're talking about is as you cure the material in this layer, that material then sticks to this glass window, and this glass window underneath is where light travels through and hits the object and cures the material. So I'm going to talk about another method that was used to eliminate this problem, and that is called CLIP, continuous liquid interface printing. And it has allowed for significant improvements in print speed, as well as eliminating this problem. And the reason it has sped up this process is because you no longer need to do this pumping action. So you can actually continuously withdraw your object from this pool without needing to go back and forth and to peel the solid object off of the membrane. So how do they avoid sticking of the object to the glass window? Well, this is how. You remember from free radical polymerization that the way these materials polymerize is that you have a radical molecule that hits your monomer. The monomer double bond breaks into a single bond, and therefore it extends with that radical. And now the entire molecule here is a radical because it has a free electron. One of the carbons has been engaged with the radical, and then the other has a potential for one electron to bind to the next unit, and that's how that one then activates the next monomer, and the propagation continues. Okay, so this propagation continues, and the monomer chain reaction goes all the way until you stop it. Now, one way to terminate this is to use oxygen. Oxygen is an inhibitor, and what it does is that it becomes two radical oxygen atoms. We call these radical oxygen species, and they actually attack this electron here, and therefore they quench this chain molecule by terminating this. So once they terminate it, or in other words, they inhibit the reaction, the process no longer continues. And as a matter of fact, they are so abundant in the environment that they don't even allow the free radical to attack a monomer. They immediately quench the radical. So oxygen is a great way to inhibit this process, and as well as to terminate it, but also to inhibit it first place. And therefore, what a group of researchers in the US found was that if they could actually have a window that's oxygen permeable, so it has a transparent window here that is permeable to oxygen, so it allows oxygen to pass through. In the vicinity of this window, the very close neighborhood, you can have an oxygen-rich layer just next to the window, and that oxygen-rich layer, which is constantly maintained with oxygen from the environment, because this window allows oxygen to get through pretty easily, would actually quench and inhibit any sticking to the glass. More basically, what that means is that no cross-linking would happen right next to the glass because of the abundance of oxygen coming from this oxygen permeable window. And so, although you get curing a little bit further away, but at the immediate neighborhood of this window, which is where we care about, you don't get any cross-linking, meaning that it doesn't stick to the window. And therefore, instead of doing this pumping process, you can continuously withdraw this object just because of this particular technology that you're using that allows oxygen to quench that layer and to avoid sticking. Now, what we call this oxygen-rich layer is the dead zone. This dead zone is the region where you don't get any cross-linking or any polymerization because, as the name suggests, it's a dead zone and the oxygen there doesn't allow any polymerization to initiate. So we call this continuous liquid interface printing because, of course, there's always a liquid interface here that is not allowed to transform into a solid, and it allows for a continuous printing process. Okay, still this process is layer by layer. Okay, so you still need to do one layer at a time, but it's much faster because you don't need to be worried about the mechanical requirement of peeling this object off. Okay, so now I'm going to talk a little bit about elastomers and how we process them. But before that, I'm going to have a little quick note on manufacturing in general. So manufacturing, and typically the way that we look at manufacturing nowadays, is a process of mass production. Okay, when we think about mass production, we think about these, since the day of these Model Ts, we have very large number of products produced in a single factory floor, and they're all repeat units. Okay, so it's mass production process, but they all look the same. They all have the same specs. And this has been the way manufacturing has been. So if you remember the conventional processes, extrusion, injection molding, they all do a repeat task of making many of the same object, one after the other, and so on and so forth for a very long period. But to customize is different from to mass produce. To customize is to have this car here have a different setup from the other car and from the other car there. So what we have with manufacturing processes in the conventional sense doesn't allow that. Now, 3D printing has come to change that really. So additive manufacturing has allowed us to make these aligners. You might have come across this company Invisalign. What they do is they make these aligners for your teeth that are custom designed to the specific geometry of your teeth, patient, and every single one of these is different from the other. Okay, so it's customized, personalized to the patient. Okay, so it's patient specific, and they need to make hundreds of thousands of these every day. So how do they do this? The way they do this is with 3D printing. They indeed have large factories of 3D printers that are capable of producing customized objects at a fast pace. Okay, so this is really happening where you have large volume production at very low cost of customized geometry. And this is really where we're going with 3D printing, is mass production, but with customization. So mass customization is where we're really going. And a lot of these printing processes print the polymers directly, but a lot of them are part of a process that then is used to produce these. So for instance, to make these aligners, you can directly print them, or you can actually print the inverse of these and then use other processes like thermoforming in this case to transfer the shape and geometry of this to the actual physical object, which is this thin silhouette. But in any case, I just wanted to bring this point up that the main advantage of 3D printing really in the future of manufacturing is that it brings customization to mass production, and that's where we're going. So adding that to machine learning and artificial intelligence allows you to then fully automate the system and the manufacturing loop in order to be able to do whatever you really want to do in terms of the geometrical and design freedom. Okay, so now we're going to talk about elastomers and vulcanization. So this will be the last bit that we're going to cover. So we discussed a couple of different cross-linking routes, and elastomers have a special one that's a bit different. And the way it works is that, and this was first found by Charles Goodyear. So he actually, I mean, the company Goodyear is named after him. He actually found that adding sulfur to this mixture of polymers and monomers and polymer chains allows for a much better elastomeric behavior. What we mean by that is that it allows this rubber to elongate much more and to then go back to its initial state once the stress is relieved. So it gives it the actual elastomeric performance that you want it to have. Otherwise, if you didn't do this process, which is called vulcanization, it would still be rubbery and deformable and elongate quite a bit. But the problem would be that once you elongate it at very high stresses, it would no longer go back to its original shape and form. So what happens here is that with vulcanization, it becomes stiffer and it also becomes more elastic. Now we'll see how that affects its stress strain behavior. But before that, let's see how it works. Okay, so the idea is that you only have to add a controlled amount of sulfur to this mixture of polymer and monomer chains to be able to achieve this cross-linking state. So this is, again, a cross-linking process that we're looking at. And it's actually a permanent one because, as you can see, these are all permanent covalent bonds here. What it does is that the sulfur added here, it opens up that double bond, so it becomes a single bond, and then two of these sulfur atoms will sequence a chain of these that can have as many as, you know, M and N in this case, sulfur atoms, connect these two chains together. Okay, so what happens is that you actually, rather than having these long polymer chains, you've now cross-linked them together to produce a much stronger network, like you do with a lot of the other polymers that we've seen here. And this is a sulfur system. There are lots of other ones like the peroxide system, the urethane system, and the metal oxides. So the idea is, again, to cross-link these molecules together like we do in a lot of the other cases. And as you can see here, it's a chemical reaction. And so once you add the sulfur, it acts like a basically a curing or a setting agent, a cross-linker. And it's a chemical reaction that's permanent. So once you've done this, you can no longer melt the tire down and make another tire out of it because it's a thermoset. And you've achieved a thermosetting polymer here. So what this means in terms of the mechanical properties is that you get a much stiffer rubber, okay? And it again has very high elongation values, but then again, what's interesting is that in comparison with unvulcanized rubber, at every point here you can see that the stiffness, the slope is going to be larger, and then also in general it's going to have, you know, a much stiffer behavior, meaning that for the same amount of strain you need to have a lot more stress exerted on this. So Again, they can achieve very high elongations, as you can see here, many times their original length. In this case, it's like 6 times the original length, but then it also now allows it to go back to its original state once you've relieved this stress, okay, which is exactly what we expect from an elastomer. Okay, so just to summarize and compare these, polymers in comparison with metals and other materials, they typically have smaller elastic moduli, they have smaller strength and yield stresses. They also have, smaller KCs or basically hardnesses, and the temperatures, the operational temperatures are also going lower. So that's typically what you have here with polymers, and you've seen this throughout, is that they actually have small stiffness and strength. But then when it comes to deformation, well, first of all, they typically have much higher elongation at breaks, but as you could see, it's really temperature and time dependent when it comes to these deformation and stiffness and strength. You have a very significant temperature dependency. So what they really do these days with polymers is they typically reinforce them with other materials. So you can have a mesh and then use your polymer as a filler. So you always have a backbone that acts as the stiffening, or the rigidity basically comes from that. And then you have the polymer that gives it the elongation and deformability that it requires. Now, apart from these general properties, each of these classes of polymers, again, you see here, thermoplastics and thermosets, and elastomers that can be thermosets if they're vulcanized, each of them have their own specific sorts of trends. So when it comes to stiffness, strength, and temperature, basically operational temperatures, you typically see that thermoplastics have smaller strength and stiffness, and thermosets usually have larger strength and stiffness. And the reason for that is that thermosets, because you use the curing agent and they cure to a very high degree, the cross-linking is really significant, whereas thermoplastics, they usually have a plasticky behavior, and they usually have lower degrees of cross-linking typically, whereas thermosets can become really highly cross-linked and stiff because of the nature of the chemical bonding, and that it happens more uniformly and more abundantly. But when it comes to KC, it's different actually. So thermosets have a smaller one than thermoplastics, and you can expect that because thermoplastics have a plastic behavior and thermosets are a bit more brittle and rigid. When it comes to reforming and recycling, as you know, thermoplastics are the only ones that you can recycle and reshape into a different object. Thermosets, in contrast, can't do that because, as I've mentioned many times, there's a permanent reaction that produces thermosets, and so there's no way that you can go back and basically revert that permanent process. And then elastomers basically are extremely high elongation at break and highly deformable materials that can be thermosets due to the vulcanization. And the good thing about them is that they have a reversible strain. So rather than experiencing necking like plastics do, they extend and can go back to their original length pretty easily. Okay, so this is the last slide of this series on polymers. I hope you've all enjoyed the discussions that we've had, as well as the in-class chats and in-person sessions. And I hope you have a wonderful break, and also have a great exam series coming up in a couple of weeks. And I hope that you all find the exam also at a good level, and you're able to respond to the questions, as I'm sure that you've been reviewing the quizzes. The final exams will be of the same style as I've mentioned in the class, and also of the same material and content. So hopefully you're all going to do very well. If you have any questions, do post it on the forum. If there's questions that you do not want to share with others, definitely reach out via email to me at h.haydari@qmul.ac.uk, and I will keep in touch with you in the next couple of semesters, as I hope you will do. Have a wonderful rest of the day and take care. Bye.